physics with Mr. Clapping. This can't be good. Alright, capacitors. Capacitors. Well, let's do just the concepts first, or at least some of the concepts. We just finished resistors, and after resistors we're going to do capacitors. So the idea is that you take a metal plate. Let's see if we can draw it. Here's a metal plate. You draw another metal plate. So you have two metal plates, and then you connect these two metal plates to a battery. Let's put a switch here. Here's the battery. That's not bad. We have a positive terminal, we have a negative terminal, so let's put plus, let's put minus here. Alright, so what we will do now is we're going to close the switch and we'll analyze what's happening in a circuit, just conceptually. So suppose that we do just that. We close this switch, and now the circuit is, well, not quite open. I mean, not quite closed, because it is obviously open right here. We have air in between the two plates. There's just air here. So let's actually state this, that we have metal plates, and then we have air between the two plates. Once we close the switch, the positive terminal of the battery is going to attract the negative charges, the electrons, in a wire, and so we're going to have an electron that flows in this direction, an electron here that flows in this direction towards the positive terminal of the battery. Here's going to be another electron that moves in this direction, here's another that moves, another that moves, right? All of these electrons here in this wire will be attracted towards the positive terminal of the battery. And of course the plate is connected to the wire, so the electrons in the plate will also be attracted to the battery, to the positive terminal of the battery. And that means that some of the electrons will move away from the plate, meaning that the plate itself will lose electrons, therefore become positively charged. And so now we will have some charge Q on this plate, positive Q. Now the other terminal of the battery will do something very similar, but instead it will push charges into this section of the circuit. So the electrons will be pushed. This electron will move in this direction, this one will move in this direction, this one will move in this direction, this one will move in this direction, and so on, until finally some electrons here towards the end will move into this plate. And if they move into this plate, then now we're going to have an excess of negative charges, and so you're going to end up with some negative Q on this plate. Now note that as you pile up more and more charges on this plate, it is more and more difficult to add more charges, right? Suppose that you have 4 negative charges here, and then you wish to put the 5th one, and you put the 5th one on. Then once you have 5 negative charges in here, it'll be even more difficult to put the 6th one on.
I'm going to take care of you.
Alright, thanks, Anya.
You could just be crying.
Oh, yeah, Daddy's doing some work.
Oh, yes.
Let's go have some tea.
Oh, yes. I'll put the
Okay, so the more charges you have on the plate, the more difficult it is to add more charges into the plate, until eventually the resistance here from these charges, the opposition from these charges, is so great that no more charges can be packed, and so you reach some maximum Q. Now, of course, how many charges you can pack into this plate will depend on how strong the battery is. There's a certain voltage at the battery, and the bigger this voltage at the battery is, the more of a push you will have to put the charges on this plate, and likewise the more of a pull you will have here to pull the charges off this plate, leaving the positive behind. So this is, roughly speaking, the way you would charge a capacitor. Now suppose that you have a capacitor like this that is already charged. We have a positive charge here on this plate, and then a negative plate here. Let's say the capacitor that is charged, and let's say that this thing is now connected to a bulb. All right, so let's say that this is a light bulb. And there's some Q, so some plus Q, some minus Q, and then let's say you close the switch, what happens is the charges will flow, and so you're going to have a current I that flows through the bulb, and, well, all right then. So I'm using a conventional current here, but if you wanted to, we could do this in terms of the actual current, so maybe I'll get rid of this and I'll indicate it this way. You're going to have a current, you're going to have electrons that flow out of this plate, flow through the bulb, and then flow into the positive plate. And so there's going to be current I. And, well, obviously, if charges will flow through the bulb, then the bulb would light up. And so in that sense, the capacitor can behave sort of like a battery. It is not the same thing as the battery. It operates on different principles than the battery, but it can behave like a battery. In fact, the symbol for the battery is this, where you have a long section here and the shorter one. This is plus, this is minus, so this would be battery. And symbol for the capacitor is just this, which is, well, similar to the battery. They're not the same symbol, but they're kind of similar. So this would be the symbol for the capacitor. All right, so we have the concepts more or less. Now, well, we've stuck kind of, there are more concepts, but we sort of understand how, what's happening here once you take a capacitor and connect it to a battery. Now note that this process of charging a capacitor is going to be very, very, very quick, depending on the size of the capacitor and the battery here. This could be microseconds or nanoseconds, so it doesn't take long. I mean, it could be milliseconds, but the point is that it doesn't take long for the capacitor to charge. All right, now if we have a charge, if we have one plate here and it has a charge, certain charge Q, and we have another plate here and it has a charge Q, one is minus, one is plus, and note that these two Q's will always be the same, and they have to be the same because it's the same battery that sets up the charges. So here's a capacitor. We have a positively charged plate, we have a negatively charged plate. It should be obvious that what we have here is an electric field that is present between the two plates, and that electric field points from the positive terminal to the negative terminal. So there's an electric field on the inside of the capacitor. Now, every time you have an electric field, you can also draw the potential lines, the electric potential lines, right? You may recall that if the electric field points like this, then you can draw potential lines like this, as long as you draw them to be perpendicular to the electric field. So here you would have some V1, some V2, and some V3. And this would be decreasing in the following way. The electric potential always decreases in the direction in which the electric field points. And so going back to the capacitor setup here, I would have some potential at this plate. Let's call this V1, and I would have some potential, electric potential at this plate, V2, and therefore I would have some potential difference between the two physical locations. There would be some delta V. And so every capacitor, I'm going to put it here, will have some potential difference, delta V, between the two plates, as long as there are charges on the two plates. And every capacitor will also have electric field between the two plates. Let's label this as E. All right, so now we have that. The last thing we'll do in this little video is we'll try to determine how the current and the charge and the potential difference behave here in this capacitor while the capacitor is being charged. All right, so let's make some room. We're going to get rid of this, or rather, I should probably just move this. So I'm going to keep it here, but I'm going to move it up. Okay. Let's see. Okay. Let's start with the charge Q. So here's charge Q. Let's see what this charge Q does with time. Rather, let's see how it behaves through time. We will start at, so initially we want to consider a point in time where the capacitor is not charged, so the switch is open. We're thinking about this circuit here. Initially, when the switch is opened, there's obviously no charge on either plate, and so I have to start at 0. And then as I flip the switch, the charges start to flow and they start to pile up on both of the plates, and therefore the charge here will increase with time, so I have to have an increase. Now the question is this a linear increase, or does this thing level out at some point? And you should intuitively see that it is going to level out at some point. So I'm going to draw this and I'll explain why that's the case, but it will level out, and in fact you will reach some maximum charge Q. So I'm going to put here Q max. So there's some Q max. Now the reason why this has to curve like that is because the more charges you pack on the plate, the more difficult it is to add more charges. And so for that reason, this thing has to curve out like that. Now, once we have an idea about how this graph should look like, this in fact is going to be an exponential function, but we'll get to that later. Once we know how the Q behaves, then we can figure out from this graph how voltage will behave across the capacitor. So let's draw another graph here, potential difference versus time. Well, if there is 0 charge at the plates in the beginning, then there will be 0 voltage in the beginning as well. And the reason for it is this. Potential is KQ over R. This was the equation for the electric potential, and it is from the electric potential that we get potential difference. Now, if Q is 0 on both plates, then you would have potential and potential difference between the two plates being 0 as well. So initially, if there is no charge at either one of the two plates, then there will be no potential difference between the two plates. But then as you start piling up the charges on the two plates, the potential difference shows up, and it's in fact going to increase. Right, and the bigger the plus, the bigger the minus, and therefore the bigger the potential difference between the two. And so you should expect this graph here to mimic the graph of the charge above. And this will also level off at some maximum voltage. Now the maximum voltage you could have across a capacitor is going to be equal to the voltage of the battery. You cannot put more voltage into the capacitor than you have at the battery that charges it. And so this is going to be the voltage of the battery. Right, and finally we can figure out how the current will behave in this circuit. And so we started with no current because initially the switch is open and there's nothing flowing, and then we flip the switch, the current is going to increase, but we know that eventually this current has to decrease, and in fact eventually it has to stop, because given enough time you reach a maximum charge that you can possibly pack into the plate of a capacitor. That's actually not quite true because, well, at least in theory, because this is an exponential function, you never reach that Qmax, but so since there is a maximum charge to which you could charge the capacitor, assuming that you can get to that maximum charge, at that point, current would have to stop. And so we know that eventually this current has to be 0. So we started with 0 current, and then we end with 0 current. That means that we have to have some kind of a peak here, some kind of a hill of a function. Now, as it turns out, the increase is very, 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 very sharp. We reach some maximum current, and then this thing decays, and it decays exponentially. So so this is the graph. Now, what we often do in physics and science and engineering is we simplify our life a bit, and in fact, this is precisely what we'll do here with this initial part. We're just going to get rid of it. So I'm going to select it. Let's take that, get rid of it, and now we're going to select this graph, and we're going to move it to the left, and this is the graph we have for the current, and that should do. Just fix what I have here. All right, well, there it is. So we have some maximum current I max in the beginning, and then that current falls off along the exponential function until eventually the whole show stops, and then the capacitor is no longer charged. Okay, so these are the initial concepts about the capacitor that you need to understand.